Ever pondered whether wormholes, bridges through space-time, truly exist? If you're a fan of science fiction, you've likely encountered the concept. They're often portrayed as cosmic shortcuts, warp-speed passageways connecting distant corners of the universe. But what exactly are wormholes? The term wormhole may conjure images of gigantic space slugs or interstellar creepy crawlies, but fear not, the reality is far less squirm-inducing. Wormholes are hypothetical features of the universe, a sort of tunnel through the fabric of space-time. They're like cosmic shortcuts, passages that could, in theory, allow us to zip across vast interstellar distances in the blink of an eye. Think of space-time as a two-dimensional sheet. Now imagine bending that sheet so 2 points touch and then punching a hole through those points. That's a rudimentary way of understanding wormholes. They offer a potential route from point A to point B without having to traverse the space in between. But it's not as simple as it sounds. These aren't your run-of-the-mill tunnels. Wormholes are regions of space-time with tremendous mass, and they're incredibly unstable. One slight disturbance and they could collapse, closing the shortcut. And there's also the question of size. Many theorists suggest that if wormholes do exist, they might be microscopic, far too small for us to perceive or travel through. Moreover, the concept of wormholes arises from Albert Einstein's theory of general relativity, a mathematical model of how gravity works. And while this theory has been proven to accurately predict a lot of phenomena, it doesn't necessarily mean that wormholes exist. They remain purely theoretical, a mathematical curiosity that has yet to be observed in the real world. So the question remains, do wormholes really exist? Let's delve deeper into the science behind this fascinating concept. To comprehend wormholes, we first need to grasp the concept of space-time. Now imagine a tablecloth stretched out flat. That is our universe, and the fabric of this cloth represents space-time. It's a four-dimensional fabric that combines the three dimensions of space, length, width, and height, with the one dimension of time. The interesting part is that this fabric isn't static. It can warp and stretch, much like our tablecloth. This idea is the essence of Albert Einstein's theory of general relativity. Einstein proposed that matter and energy, the stuff that makes up everything in our universe, cause space-time to curve. Think of placing a heavy ball on our tablecloth. The cloth dips under the weight, creating a curve. This is the effect that matter and energy have on space-time. Now, if you were a tiny ant walking on the tablecloth, your path would follow the curve created by the ball. This, in essence, is how gravity works. But what if this curvature could be so extreme that it forms a tunnel or a shortcut through space-time? This is where the idea of wormholes comes in. A wormhole, in theory, is a passage through the fabric of space-time, connecting two distant points in the universe. Imagine poking two holes in our tablecloth and then folding it so the holes line up. An ant could then walk straight through, bypassing the surface of the cloth entirely. That's a rudimentary way to visualize a wormhole. However, it's important to remember that all of this is purely theoretical. As of now, we have no concrete evidence that wormholes exist. They remain a fascinating concept born out of our understanding of space-time and the curvatures within it. Given the possibility of curved space-time, wormholes may indeed be possible. But where does that leave us in terms of actual evidence? The existence of wormholes remains unproven, but that doesn't mean scientists aren't looking for evidence. The quest to prove or disprove their existence is one of the most intriguing pursuits in modern astrophysics, as it opens up the possibility of shortcuts through space and perhaps even time. Currently, researchers are exploring various avenues to detect these elusive structures. One such method is the hunt for gravitational waves. These ripples in the fabric of space-time, first predicted by Albert Einstein over a century ago, were confirmed by observations in 2016. The collision of two massive objects like black holes or neutron stars can generate these waves. Some scientists propose that if wormholes do exist, they might also produce detectable gravitational waves. However, the search is far from straightforward. Wormholes, as theorized by physicists, are incredibly unstable. They blink in and out of existence in the tiniest fractions of a second. This makes them nearly impossible to spot, even if we knew exactly where and when to look. Another challenge is the theoretical need for exotic matter to keep a wormhole open. Exotic matter is a type of substance that would have negative energy density and large negative pressure. This is a concept that exists in the equations of general relativity but has never been observed in the physical universe. In other words, we have yet to discover any type of matter that fulfills these requirements. Despite these daunting challenges, the scientific community remains undeterred. We are in the early days of gravitational wave astronomy, and our understanding of the universe is growing every day. Who knows what discoveries the future might hold? While the search for wormholes continues, it's important to remember that science often takes time to unravel the mysteries of the universe. The quest for knowledge is a journey, not a destination, and the potential existence of wormholes is just one of the many fascinating questions we aim to answer. As we continue to explore the universe, what might the future hold for our understanding of wormholes? Our journey into the future of wormhole research could lead to groundbreaking discoveries. Imagine for a moment a universe where wormholes are not only real but also accessible. This would revolutionize space travel, transforming our perception of distance and time. We could potentially hop from one corner of the universe to another in the blink of an eye. On a deeper level, the discovery of wormholes could provide us with unprecedented insights into the nature of the universe itself. These cosmic shortcuts could be the clues we need to finally unify quantum mechanics and general relativity, the two pillars of modern physics that have long resisted integration. We are living in an exciting era of technological advancements and theoretical physics breakthroughs. With more sophisticated instruments and refined theories, our ability to detect and understand wormholes is ever increasing. Whether wormholes are fact or fiction, the quest to understand them continues to push the boundaries of our knowledge and ignite our curiosity about the universe.